Hey guys, welcome back to The Explainer. Grab those lab notebooks, because today we're doing a massive recap of our recent lab work. I'm going to be walking you through all those fascinating chemical properties we've been observing over the past few weeks. Our goal today is to completely demystify acids, bases, and salts. We're not just looking at abstract textbook concepts here. We're taking our actual lab observations and seeing exactly how they play out in the real world. Okay, let's dive right in. Let's kick things off with a super relatable case study. Imagine this. Someone in your family is dealing with a terrible case of acidity after totally overeating at a big holiday dinner. You rush to the kitchen to help. Do you grab lemon juice, vinegar, or a baking soda solution? Kind of sounds like a trick question, right? But to actually answer it, we've got to look at what our recent lab results tell us is happening on a fundamental chemical level. Before we go curing anyone's stomach ache, let's do a really quick refresher on those basic sensory properties we've all experienced. You know the drill. Acids, like the citric acid in a lemon, have that unmistakable sour taste. And in the lab, they turn blue litmus paper red. Bases, on the flip side, are bitter. Think of soapy water. And they do the exact opposite chemically, turning red litmus paper blue. It's just a beautifully symmetrical relationship. But what's really fascinating is how these properties pop up when we aren't even trying to do chemistry. This brings us to case study number 2, the curry stain. Have you ever spilled curry on a white shirt? It leaves this bright yellow stain because of the turmeric. But watch what happens when you try to wash it out and scrub it with soap. It suddenly turns a dark reddish brown. Why does it do that? Well, soap is basic, and turmeric actually acts as a brilliant natural acid-base indicator. The crazy part is, when you rinse the shirt with a ton of water and wash that basic soap away, the stain goes right back to yellow. You are literally running a chemical indicator test right in your laundry sink. Okay, let's look at the actual data we pulled in the lab using some of our more formal synthetic indicators. Look at the stark contrast here. Phenolphthalein, for example, stays totally colorless in an acid, but the second it hits a basic solution, boom, it turns a bright, vivid pink. Methyl orange gives us another awesome contrast, shifting to entirely different colors depending on the media. By tracking these precise color shifts, we essentially created a foolproof map for identifying unknown liquids. Now, we obviously don't just use our eyes in the lab, and that leads us to something genuinely surprising: olfactory indicators. These are substances whose actual smell changes depending on whether they're in an acidic or basic environment. Remember testing those cloth strips treated with chopped onions, vanilla extract, and clove oil? When we added a base, like sodium hydroxide, the classic smells of the vanilla or clove were completely wiped out. But in an acid, the smell stuck around. It's just a really cool reminder that chemistry engages all of our senses. So when the professor hands us an unknown substance, how do we figure out what it is without, blowing something up? Here is the exact step-by-step methodology we perfected. Step 1, place a few drops of the unknown on a watch glass. Never taste it, never touch it. Safety first, always. Step 2, apply one of our trusted natural or synthetic indicators. Step 3, carefully watch for any color shift or odor change. And finally, step 4, match that observation against our data to classify it as an acid or a base. It's clean, it's elegant, and it's perfectly safe. But what happens when we smash these two opposing forces together? That brings us to a massive concept from this week: the neutralization reaction. When you combine an acid and a base, they literally cancel each other out, producing salt and water. And this brings us right back to our very first case study. If your stomach is turning out way too much acid, you definitely don't want to add lemon juice or vinegar. Those are acids. You want to introduce a mild base, like baking soda, to trigger a neutralization reaction right inside the digestive tract. It turns that painful excess acid into harmless salt and water. Case closed. But acids don't just react with bases. They get pretty wild when you introduce metals. Remember our setup with the zinc granules and the dilute sulfuric acid? The second that acid hit the metal, we saw this rapid bubbling on the surface. That was the metal displacing hydrogen atoms from the acid to form a salt while kicking out pure hydrogen gas. We even routed that gas through soap to make bubbles, and when we brought a burning candle near them, pop! The hydrogen burned with this tiny, distinct little explosion. For sure, that was one of the coolest things we observed all week. So we've seen all these macroscopic effects, right? The vivid colors, the changing smells, the loud pops, the neutralization. But why exactly is this happening? What is the core mechanism? It all boils down to ions. When dissolved in water, acids generate positively charged hydrogen ions. That is the absolute true source of all their acidic properties. Bases, on the flip side, generate negatively charged hydroxide ions. So when we trigger a neutralization reaction, We are quite literally just crashing those hydrogen and hydroxide ions into each other to form H2O, just water. And this completely explains why we have to be so incredibly careful in the lab. Getting those ions to separate in water is a highly exothermic process, meaning it releases a massive amount of heat. You'll definitely recognize this warning sign from our concentrated sulfuric acid containers. Here is a vital heads up for all of us. When diluting an acid, you absolutely must add the acid to the water, very slowly while constantly stirring. If you mess up and pour water directly into a concentrated acid, the sudden, violent heat can cause the whole mixture to flash boil and splash acidic drops right in your face. Definitely not something we want. Since we know acids generate hydrogen ions, how do we actually measure the exact strength of an acid or base? Enter the pH scale. The scale ranges from the deep reds at 0, which is insanely acidic, all the way up to the dark blues and purples at 14, which is highly alkaline or basic. Right in the middle at 7 is perfectly neutral, just like pure water. This scale is basically a power meter for the concentration of hydrogen ions. The higher the concentration of those hydronium ions, the lower the pH value drops. Using universal indicator paper to test household items and seeing them line up perfectly across this color spectrum was incredibly satisfying. Let's bring this all together and look at how our lab data solves real-world chemistry. We've already cracked the stomach acidity case. We confidently know to use a base to neutralize biological acid. We decoded the Curie stain, proving soap acts as a basic indicator on turmeric. But let's look at a third, absolutely crucial case study: acid rain. When atmospheric pollution drops the pH of rainwater below 5.6, it becomes highly acidic. When that rain flows into our rivers, it drastically lowers the pH of the entire body of water. Since living organisms, including us, need to operate in a very narrow pH range, this drop makes aquatic life nearly impossible. Understanding this chemistry literally empowers us to tackle these massive environmental threats. Which leaves me with one final, really provocative question straight from the margins of our textbook. We just saw how remarkably sensitive biological life is to pH levels. Well, the atmosphere of our neighboring planet Venus is made up of these thick, heavy, yellowish clouds of concentrated sulfuric acid. Based on everything we've observed in the lab about how highly reactive, corrosive, and downright dangerous strong acids are, do you think life, as we know it, could possibly exist on that planet? I'm going to leave you to think about that on your way to our next class. Thanks for hanging out for this explainer recap, and I'll see you guys back in the lab.